everyone. So, last class we have seen some examples on ANOVA, like how we can solve for ANOVA, how we can find out whether the means of the different populations are same or they are not same with a particular significance level. That is what we have seen. And till last class what we have discussed is that if you have noticed, all the samples that we have considered, all the samples are of same size. Remember, all the samples we have taken as n, so small n basically. So, all the samples were of same size. So, today we will just take a slight variance of that. So, where does it is not always possible that always we take a samples of same size, but it is advisable for ANOVA. It is really advisable if we, it is better if we take samples of the same size, but sometimes it is not possible. We have to take samples of different sizes. So, today we will see the this computational formula if we use samples of different sizes. Basically, we call that as unbalanced data. Okay. So, this is what we have already seen. In essence, given a populations, a single factor of A levels, we have to calculate 2 estimate of sigma square, sampling variance between groups with A minus 1 degrees of freedom, that is from that we get is MS treatment. So, then sampling variance within group with n minus a degrees of freedom, that is we call it MSE. Then the F is MS treatment by MSE. Okay. So, now in some single factor experiment, the number of observation taken within each treatment may be different. Okay. In some cases it may not be same due to many other factors. Of course, our target should always be try to keep the sample size same, because there are many what to say. First, now you may ask why we should keep the same equal sample size. First of all, see, when you have assumed that remember when we have tried solving for one way ANOVA, we have taken one assumption. We have taken 3 assumptions basically. Out of them, one assumption is that all the populations variance we have considered it to be equal, that is sigma square, isn't it? All the population variance we have considered it to be equal, that is sigma square. And for that sigma square, we found out a pool variance estimate. So, now if we it is sometimes it is really not possible that all the population variance may be exactly same. It is not exactly same, but when we have say same means it is similar and the same range maybe, but sometimes it is that it is not possible to be in the similar range. Sometimes it deviates a bit from the range. So, if we take the size of the sample as same, this slight deviation from this slight deviation of variance of the this population between different samples, this will not have a very bad effect, means this will not make our results incorrect. Okay. This will not make our results, this will not make to lose our precision of our results. But if the sample size differs, then what happens, slight variations of this slight change of variation of this different populations, it may reflect too much on our end results, and which makes our result imprecise. Okay. So, as I told you, it is really not possible that all the variance will be almost same, there will be slight changes. So, that is why it is always better if we take samples of the same size, because slight variations, if the sample sizes are not same, it will be reflected in the results, and basically we will not get a result which we can be reliability of the result will not be high. Okay, the result will not be precise result, there will be error to it, our type 1 error will increase, and type 1 error increase means definitely that is not something which we desire. That is the first thing. Second thing, one more important thing is that if our data is balanced, if our sample size is n for all the samples, then what happens, our power is also maximum. That is one way. It see, if our type 1 error remains low, definitely our power will also be more, isn't it? So, when we for unbalanced data, what happens, our type 1 error increases, accordingly our power also reduces. So, that is it is a direct connection basically. Anyway, I will not show you the total derivation of how the power increases for a stable data and unstable data, how power goes down. That is that I will not deduce and show it, but you know how to calculate power. We have seen it for one population, we have seen it. Similar way it can be done actually, and I suggest you not to try also those simplification, because it is a long computational law, and there are many softwares to that which will do that. When softwares are available, why unnecessarily try doing lots and lots of calculation to find that. So, there are many softwares. By the help of software you can just feed this data and you can see for the thing for the same significance level for balanced data and unbalanced data, the change of the power. Okay. So, now as I told you, this is called unbalanced design. In such cases, slight modification must be made in the sum of the squares formula. When that is cases is when our design is unbalanced, whatever formula for f we have, there will be a slight modification in the formula, and that is obvious, right, because there in our formulas what we have used, we have directly used n, small n. Now, here for all the different samples there will be different n, it will be n I basically. Okay. So, you see here how is the change in the formula. Number of samples is a, number of observation in the ith level is n I. Okay. So, then total number of observation is again capital N here, capital N is summation of all n I is equals to 1 to a, that number of levels. So, earlier for n is what is capital N directly we could write a into n, total number of levels into the number of observation in each level, a into n. So, now n will be this. So, jth observation in ith sample, that is same, and j will go from 1 to n I. Okay. And sum of n I observation in ith sample. So, sum of n I observation in ith sample, here basically j will go from 1 to n I. It will not, j will be not from I is equals to 1 to n, it will go from 1 to n I. For each level there will be different n, maybe same, but different. For unbalanced data, this is the formula. Instead here I am writing it as T I. Actually, if you can remember, sum of all the observations in the earlier formula what I was using is y I dot. Remember, I was using is y I dot. So, actually now the coming formula which I will be using this y I dot, this dot things, it becomes difficult to represent. So, I have just used a different nomenclature, that is all, but it is the same thing. Okay. So, I am using a different nomenclature, that is T I. So, do not get confused, it is the same thing, just I am using a different variable, that is all. So, T I is j is equals to 1 to n I y I j, then the sum of all n observations, sum of all n observation, remember it was y double dot, I used y double dot in the earlier. So, instead of that I have used the simple T. T is, it will be summation of I is equals to 1 to a, I is equals to 1 to a T I, and this I is equals to 1 to a, j is equals to 1 to n I y I j. Fine. So, now since this is for this difference, so this difference will be reflected in the computational formula also. Okay. So, how it will be reflected? So, our SST is now this. This you can do by yourself and you will see. In SST, earlier what was in SST? In that place, now here you see y I j will be, j will go from j is equals to 1 to n I. For each I there will be a different n I, isn't it, n 1, n 2, n 3. So, there will be a change accordingly. You yourself will be able to solve a simple calculations. So, you will get SST is this. Okay. So, SS treatment, similarly SS treatment is this. I am not showing the derivation, you will be able to do it by yourself. So, this is the SS treatment. Fine. Then once we know SST, once we know SS treatment, again SSE we do not need to separately find it out. SSE is nothing but SST minus SS treatment. What is SST? SST is the overall sum of squares, right. So, SS treatment is the sum of squares between treatment, or sum of squares within group I can find out from this formula SST minus SS treatment. Okay. So, once I know SSE, once I know SS treatment, I can find out the MS treatment, I can find out the MSE, isn't it. What will be MSE? MSE will be SSE minus total samples n minus what, n minus a, and here SS treatment will be a minus 1. So, that gives sum of square divided by the degree of freedom gives us the variance estimate, is not it. So, total mean square is MST is this, SST by n minus 1, MS treatment is SS treatment by a minus 1, and MSE is SSE by n minus a. Okay. And these are same, just that there will be a slight difference of this value in this SST and SS treatment. You can just take the earlier formula, and that earlier formula instead of j is equals to 1 to n, there you just replace it j is equals to 1 to ni and simplify it, you will get it. Okay. So, degrees of freedom is degrees of freedom of what? N minus 1 is the degrees of freedom of what? Which one? Do you remember? N minus 1 is the degrees of freedom of the total variability of the data. Total variability of the data degrees of freedom is n minus 1. A minus 1 is the degrees of freedom of the between treatment variable, and capital N minus A is the degrees of freedom of within each treatment. So, now take an example. First we will see the same example, which in the last class we have seen for that 60 watt bulb there were 3 different brands, and then we went on to prove that the 3 brands are we have enough what to say sufficient proof that the 3 brands are not same, isn't it. So, now though this is balanced because the sample size is same, of course, when it is a balance or non-balance, you can use the formula for non-balance, but for non-balance you cannot use the formula for balance because their n changes, isn't it. So, now we will use the same example of a 60 watt electric bulb using the we will do it the same problem using the unbalanced data. We will see we will get the same results or not. So, here for that from that we found out what is Ni is same for all this 3, and we found out the value of Ti. Ti is nothing but the summation of all these values, remember. So, now what is the summation of Yij squares? This is the sum of all squares of all the tables in the entity 1, isn't it, Yij whole square. Then this will give us the value 7045. Then what is SST? SST is Yij whole square minus t square by n. What is t square? T is 315, sum of all this. T is the grand sum, isn't it. So, 315. So, this is n is 15, we got the SST we got 430. So, similarly now we will find out SS treatment. SS treatment, this is the formula Ti by Ni, t square by n. So, we found out Ti, what is T? T is the grand total and Ti is the total of within each treatment, isn't it. What earlier for Ti we use yi dot, again I am repeating, for T we use y dot dot. So, similarly we found out using the putting the value here, we found out the value of SS treatment. Once you know SS treatment, then we can find out MS treatment, SS treatment by A minus 1, that is number of treatment minus 1. So, that is MS treatment. Okay. So, once we found MS, now we need to find out MSC. For MSC we can find out SST minus SS treatment and divided by the degrees of freedom n minus A. Okay. This we found 10 and we calculated it and we found 15.5. If you can remember, this is the same value we got when in our last class when we have solved for this same problem, 15.5. Now, with the same degree of significance, degree of significance level at 1%, we will see that this value falls in the rejection region. So, we got the same value. That means what? The formula for unbalanced data we can very well use for the balanced data as well, but the formula for balanced data we cannot use for unbalanced data. Now, we will see a different example. This is an unbalanced example. See, in the comparison of the cleaning action of 4 detergent, 20 pieces of white cloths were first soiled with India ink, some type of ink. The cloths were then washed under control condition with 5 pieces washed by each of the detergents. There we have taken 4 different type of detergents. okay, 4 different type of detergents, and we have soaked total 20 pieces of cloth with some type of ink, and for each we are trying to we will wash it with 4 different types of detergent to find out the which detergent is best basically. So, unfortunately what happened, unfortunately 3 pieces of cloths were lost in the course of the experiment. Okay. So, definitely our data becomes unstable here. We have tried to keep the stable data, because we know ANOVA it is always better if you keep the same number of samples, sample size same. So, whiteness readings made on the 17 remaining pieces of cloth are shown below. So, for detergent A we got 5 pieces, good. For detergent B we got 3 pieces, C we got 5, D we got 4, very much an unbalanced data. For detergent type of B we got 3, detergent type of D we got 4. Okay. Assuming all whiteness reading to be normally distributed with common variance, test the hypothesis of no difference between the 4 brands as regard mean with whiteness reading after washing. So, we have to test the hypothesis that the mean what to say whiteness readings, whiteness, how white is the cloth after washing is there. Suppose there is some scale, the whiteness scale, based on that scale that mean reading as is the mean reading of all the detergents same or is it different, that is what we need to find out basically. So, our null hypothesis is mean of all this is same, alternate hypothesis at least 2 are not same. Okay. So, now this is the null hypothesis, this is the alternate hypothesis, this is the significance level, consider a significance level of 5%, that is 0.05. Then degrees of freedom, of course, B 1 will be 3, number of treatment is 3 minus 1, sorry, it will be 4 different brands of detergent, the 4 minus 1 is 3, and B 2 is equals to 17 minus 4 is 13. So, we found a critical region with for 5% significance level, and with degrees of freedom 3 and 13, 5% significance level with degrees of freedom 3 and 13, the value of f is 3.411. So, now we will, this is from the table we got, this is the value, this is the critical value of f. So, any value greater than that will fall in the critical region, rejection region. So, now from this data we will find out the what value of f we get. We will find out MS treatment, we will find out MSE, MS treatment by MSE will give me the f value. So, we found out first Yij whole square, we found out this is the Ni is the sample size for these 3 samples, then we found out Ti, sum of all the samples of sum of all the observation of first detergent, sum of the all the 3 observation of second detergent, this is the Ti value, and this total is the T, okay, sum of all this is T. So, for our SST is Yij whole square and this T square by degrees of freedom, right. So, this is what our SST value, is not it. Our degrees of freedom, for degrees of freedom SST, what is the degrees of freedom? Overall variability in the data, overall variability in the data, what is the degrees of freedom? Degrees of freedom is capital N, that is whole total number of observations of all the brands together minus the number of total levels, is not it. So, here what is the total number of observations? Total number of observation is 17. And then how many brands are there? 4 brands are there, is not it. So, then we found out the SS treatment, we found out similarly we found out SSE. What is SSE? SST minus SS treatment will give us SSE. Okay. So, between detergent we found this is the sum of squares, its degrees of freedom is 3, total 4 different samples. Within detergent this variance we found is 873. This is the value within detergent is this one, oh sorry, this is between treatment, this is the within treatment 873. 873 within the treatment 873. Then this its degree of freedom is 3, this degrees of freedom is 13, then we found the f value is 1.07. 1.07 is the f value, and what is our critical region? Our critical region is 3.411. then 1.05 is something here in this range. So, it very much lies in the acceptance range, that means our null hypothesis is not rejected, right. So, F ratio does not lie in the critical region, thus there is no evidence at a 5% significance level to suggest a difference between the 4 bands as regard mean whiteness after washing. So, there is no evidence to suggest that there is a difference of whiteness in all in the different 4 bands. Okay. So, that is what we have seen for ANOVA. I don't think initially I started with ANOVA discussion telling that it is a bit complicated, but now I think you will not tell that it is complicated, it is very easy. Just find out the 2 variance estimate. One thing is complicated is to understand how to find out the 2 variance estimate. If you just try to do it using the formula, that will be very easy, but why? Do not do that. Why we are using this formula, that you should understand. That is what I have tried to explain in all the lectures. Why we are using the how this formula has come, when we are trying to find out the variance within treatment, when we are trying to find out the variance between treatment, and why we are trying to find out this 2 estimate of sigma squared, and why we have used F distribution, why does greater will give us a getting a value of F which is greater than the critical region, why does it tells this the null hypothesis is rejected. All these things you should understand, just calculating it is very easy. Okay. And this is one thing, this is what we have done, this is for basically when you try to compare the means of the different population. Now, similarly, when you try to compare the variance of the different population, there is also another technique that is called Markova. So, that we will not be discussing, this is beyond the scope of this course. So, in this lecture what we have seen analysis of variance calculation for unbalanced data, and see, as I have mentioned, for equal sample size the test statistic is relatively insensitive to small departure from the assumption of equal variance. I have mentioned this, is not it? For equal sample size, the test statistics, whatever test statistics means, here the test statistic means the F value. When we call it the test statistics, it is when I am doing chi-square distribution, my test statistic is the chi-square value. When I am using F distribution, my test statistic is the F value. T distribution, my test statistic is the T value. So, here for equal sample size, the test statistic is relatively insensitive to small departure from the assumption of equal variance for the A treatment. For the A treatment, we have assumed that the variance are equal, but small departure from the assumption that it is equal, it is, if we take equal sample size, it is insensitive to it. It will not have a it will not have a results which will give us which will inflate our type 1 error. Fine. So, but this is not the case for unbalanced data. Unbalanced data or type 1 error gets inflated if there is a departure from the assumption of equal variance. Okay. So, that makes the test, if a slight variation, if it is very sensitive to slight variation, that means what? That means the test is not robust. If it is insensitive to small variation, that means the test is robust, right. So, when our test is robust, when we take a samples of equal size. So, that is why it is always advisable to take for ANOVA, take sample size equal sample size, but always it is not possible, as we have seen in the example. So, this is these are the references, and thank you guys. So, we have completed ANOVA today. So, we will be starting a new topic in my next lecture.